the recording. And okay, so it is a great pleasure to introduce our last speaker for this year, Sambuddha Ghosh from the Shanghai University of Finance and Economics. Sambuddha was graduated in 2009 from Princeton, and since then he's interested in game theory and in political economy. And so today Sambuddha will tell us about Blackwell equilibria in repeated games. So Sambuddha, the stage is yours.
Thank you very much, Elon. So to Elon and everybody, it's a great pleasure to be here and an honor to be able to speak in this crowd. So I actually, I've 33 slides. Feel free to interrupt because I think this is not a lot of material. And, I have two co-authors in the audience. They should also feel free to chip in. So we are sorry we don't have a version of the paper ready to distribute. So this is the paper writing is in progress, but we have some of the results, and most of the results we're interested in, some getting worked on, some done. So here we are, Blackwell equilibria in repeated games. So this is joint work with Costas Cavounidis from Warwick University, Johannes Horner from Yale, Elon Solin, of course, from Tel Aviv University, and Satoru Takahashi from the National University of Singapore. And I'm Sambuddha Ghosh from Shanghai University of Finance and Economics, but you already know that. So let's get started. So this is a very basic introductory slide. And the question is, why do we cooperate? Cooperation is costly in many situations. So we cooperate because of the threat of future rewards and punishments. So cooperation takes place under the shadow of the future. And this is an idea that remains through repeated games, which is the standard model for capturing ongoing strategic interaction, right? So there are finitely repeated games, infinitely repeated games. Today, we are going to deal with infinitely repeated games. And in particular, we are going to deal with discounted infinitely repeated games. Now, I know, particularly in Israel, there's a large body of work done by several scholars on undiscounted repeated games. And, today we are not going to touch on that, but I'll get to talk a little bit about, what our philosophy is and how we see these results, okay, and why we pursue discounted repeated games. So the literature on discounted repeated games now, I'm going to just keep saying repeated games from now on, meaning it's discounted infinitely repeated. So this literature has consequences that are fine-tuned to what you do. And again, I'm using sort of abstract words, consequences being fine-tuned. So I will tell you exactly what this means, that your continuation payoff, when you're mixing, your continuation payoff actually depends on which item you mix. Your mixing throws up. So imagine you're playing left or right, heads or tails. You toss a coin. The toss of the coin determines not just your current action, but could determine your continuation payoff. So the realization of mixing will be important in several of these results in folk theorems. And these results give very permissive and very powerful, strong results, but they use fine-tuning, and fine-tuning is possible because there's precise knowledge of the discount factor. Okay, so there is, typically there's a single discount factor, but you could also have multiple discount factors, but there's always common knowledge of the discount factors. So this paper says, what if we have less precise information on how players aggregate payoff streams? So we don't know exactly the delta that we are using, okay? So let's say each person can have a different delta, and I don't know what deltas are being used. The game theorist doesn't know, the players themselves might not know. And we want to come up with a notion that preserves discounting, but without assuming common knowledge of the discount factors. So why do I want to preserve discounting? Now, you can agree or disagree with this, but our philosophy is that discounting captures something important, which is that, finite lengths of time are worth something. No matter how patient you are, they're worth something, okay? So if we do undiscounted repeated games, then, big finite chunks of time might not play a role. So we are deliberately steering clear of those models, and you'll see our model is very much about discounted repeated games, but we don't want to assume common knowledge of the discount factors. And you'll see how we modify the definition of equilibrium to take this into account. So let's look at repeated games, the notation. This is standard notation. I'm just going to go over it. There's a stage game, capital G. It includes three things. First, capital I, 1 through n, is a set of players. It's finite. Everything is going to be finite. AI is this finite set of pure actions of player I. Capital A is the cross product, Cartesian product of the AIs. GI is player I's payoff function. Okay, and it's a mapping from A, the vectors of actions, to a real number, just the felicity function or whatever you want to call it. Now, we are looking at perfect monitoring. So histories, so let's consider the repeated game at the discount factor vector delta. Now, discount vector, so I've written vector and then it shouldn't be 0, 1. It should be 0, 1 to the power of n. So there's an n missing, right? But if it's, yeah, so it's G delta. And this is perfect monitoring. So the set of histories is a set of actions that you take, right? So, and it's a union of a to the power of t. So t Cartesian products, union overall t, and that's a set of all possible histories. Okay, and sigma I maps all these finite histories into mixed actions of player I. Okay, so this is actions observable, perfect monitoring. What does player I maximize? Player I's maximized payoff is denoted as capital UI delta of sigma. So sigma is a profile of strategies, and the utility of player I when player I has discount factor delta is that term you see. So GIAT is the utility at time t, and this is discounted by delta to the power of t, not t minus 1, because we are just counting time from 0. It's not important. And it's normalized by 1 minus delta. Again, it's not important, but we're just doing it so that payoffs are comparable across the repeated game and the stage game. So the units are the same. If you get 1 at every point, then you get 1 in the repeated game as well. So let's look at a very quick standard classic undergraduate example. Cooperation in the repeated prisoner's dilemma, 2 players. Okay, 1 and 2, CD, 2 actions, cooperate, defect. And we all know you can just check D is a dominant strategy. 4 is bigger than 3, 1 is bigger than 0. It's dominant for both players. The only Nash equilibrium is 1, 1. Okay, that's a prisoner's dilemma. And let's look at the Grimm trigger strategies. The Grimm trigger strategy says everybody starts by playing C. And in any history that just contains C, we continue playing C. Okay, so if H contains no D, and as soon as somebody plays D, we switch to playing D forever. Right, so this, you can draw an automaton picture. We've all seen this undergrad stuff. And I wasn't explicit about saying we start with C, but it's implicit in the first line if H contains no D, right? So the beginning will also be C. And this is an SPNE for delta greater than or equal to 1/3. Now, the only interesting thing here is that this strategy profile is an SPNE for all discount factors greater than or equal to 1/3. And this is formalized by Friedman's folk theorem. And here I'm just going to state this again, this undergraduate folk theorem for you, but in a strong version. This is not the version we see in textbooks usually. And I'll tell you exactly why this is a strong version and how this relates to our work. So let's go to the strong Friedman folk theorem. Let n, script n, be the set of Nash equilibria of the stage game G. Now, find the worst Nash payoffs. WINE, so the worst, W for worst, I, player I's worst, NE, Nash equilibrium payoff, is the minimum of GI alpha, where alpha belongs to N. So just go over all Nash equilibrium, find the worst for I, as simple as that. Find the feasible set. So A is a set of pure action profiles. G of A is a set of payoffs of pure action profiles, a bunch of finite number of dots in payoff space in Rn. And CO is just a convex hull operator, smallest convex set containing G of A. Okay, so that's a feasible set and of the stage game. And what we are going to do is state Friedman's folk theorem next, Friedman 1971, in a slightly stronger form. This is the famous Nash-Threads folk theorem. It uses a public randomization device. Okay, so if V belongs to the feasible set, so it's a feasible payoff. And for every I, the payoff of I in V is strictly greater than the worst Nash equilibrium of I, then we can find a delta upper bar less than 1 and a strategy profile sigma star that is an SPNE for any delta greater than equal to delta upper bar. Okay, and this achieves the payoff vector V. Yes, sorry, there was a question.
Yes, I mean, so the WI&E could be higher than the min-max payoff that's normally used in the Fock system.
That is exactly right. Thank you for this comment. And we are going to get to it right after the next bullet point. So two things I want you to notice about this. The first thing I want you to notice is that the same strategy profile works for all high enough deltas. So when you look at the undergraduate statement of this in textbook, it says, well, there is a delta upper bar. And if you give me a delta that's greater than or equal to delta upper bar, then I can give you a sigma star that achieves the payoff V. But I flipped the order. So I've written down there exists a delta upper bar and a sigma star such that this sigma star works for any delta above the cutoff. So I want to emphasize the fact that Friedman actually allows you to come up with a uniform strategy profile. So strategy profile that works for all discount factors above delta upper bar. And this is a property that we will try to retain. This is a property that we will try to capture in our definition of Blackwell equilibrium. And second, the very helpful comment that just pointed out is that this is a sufficient condition only, right? So we will show you, in fact, not we, but I will show you in the slides, but it's known from the literature, Fudenberg-Maskin, that's the next slide. They show you that actually we can define something called the min-max value, which will typically be lower than this. Of course, in games like Prisoner's Dilemma, the game you just saw, here you can check 1-1, that's Nash, and it's also min-max is 1-1. So there's no difference, but in typically, okay, in games, the min-max will be lower than this. So how do we define the min-max? So we are minning I and I is maxing her own payoff. So whatever we do, I will respond with the best action from her arsenal. So we are maxing over AI inside, and outside the outer layer is we are minimizing over all possible mixed actions that are, again, this is independent mixing. So this assumes that the players do not have a secret semi-public randomization device. So if we had a semi-public randomization device where, players other than I could coordinate and toss a correlated coin, then possibly this could be lower, but we are just looking at independent randomizations, okay, over the mixed actions of the others. This is a completely standard definition of min-max, and that's WI. Now NE is gone, the index, because it's nothing to do with Nash. And it's very easy to show that every SPNE payoff vector V satisfies that for all I, VI must be greater than or equal to WI. Okay, and this is just you just deviate one shot, and suppose you're earning less than WI, then I must be doing something stupid. She should just deviate to the best response period by period. Use her opponent's strategies, track what they're going to do, play a best response to that, and then she's going to earn WI in every period by construction. So then overall in the repeated game, she's going to earn at least WI. So she was not playing optimally before. Okay, so that's actually not even SPNE, it's even in Nash that this property holds. Okay, conversely, and this is the Fudenberg-Maskin part of the fourth theorem, if F is full dimensional, so I'll tell you in a second about full dimensionality. It just means that the dimension of the set F is equal to the number of players, okay? Suppose V belongs to F, again, feasible payoff. Just like before, VI is greater than WI. Then we can find a delta upper bar less than 1, such that for any delta greater than delta upper bar, there exists an SPNE. Again, we could make it greater than equal, doesn't matter. There exists an SPNE sigma of delta that achieves V. Now, if you look at this for a second, and then we go back to the last one, you will see sigma star is chosen before the delta is handed to us. So that's the difference. Here, we are retaining the right to fine-tune the SPNE to take into account the discount factor. So this is the anything goes result. So basically, from the first result, we know that we cannot get less than WI. And this says, as long as Vi is strictly greater than Wi, so the only thing we can't say anything about is a boundary, but modulo the boundary, we are good to go. Anything goes if players are patient, right? But there is this bit of fine tuning that's happening. And let me just talk a little bit about the strategy of proof of Fudenberg-Maskin 86, and that will clarify why this is fine-tuned, okay? So given a target payoff, so suppose we're given a target payoff and a sufficient discount factor delta, we construct an equilibrium strategy using a three-phase strategy, okay? So phase one is you play the normal action. So this is normal phase. So basically you play the actions that are required to achieve the target payoff V, okay? Then suppose I deviates and you go to suppose I deviates unilaterally. So multilateral deviations are ignored, but that's not a problem because this is part of the Nash environment. So we are never concerned about multilateral actions, okay? So if I deviates, sorry, we are never concerned about multilateral deviations. So if I deviates unilaterally, all other players will play the min-max action against I for finitely many periods, okay? And this is enough, you have to play enough so that I doesn't want to cheat. And this incentivizes the normal phase, okay? And it also incentivizes the next phase. So after the punishment is done, all players other than I, and who's I? I is the last player to be punished. Whoever was the last player to be punished, that's player I. All other players will be rewarded for carrying out the punishment against I. Okay. Now, the important thing, so you can just visualize the picture. I'm sorry, I didn't set this up properly, and I can't draw the graph, but you can visualize this in your head. There's a point on top which gives a good payoff, and then we're going to min-max, and then we're going to go lower down. We're going to the southwest corner of the point V, right? So which means we're going to lower payoffs, but we are going to reward those players who carried out a punishment. So we will reward them slightly. Now the question is how much to reward them. Can we reward them a fixed amount? The answer is no, we cannot reward them a fixed amount because the amount of reward could actually depend on what they did. It depends on what min-maxing is. So suppose min-max, so let's just go back to the definition of min-max. Here we are. Suppose the minimum is attained over a pure action. Suppose in order to punish Ms. I, all the other players, Mr. J's, just need to play a pure action. Then we have no difficulty. We can give them a constant reward. But now suppose J has to mix over. There is one J who has to mix over two actions, two pure actions in order to punish I. Okay, this is quite common. Then what's going to happen is we need to adjust the continuation payoff of player I to make sure that, we need to adjust the continuation payoff of player J, the person who carried out the punishment, to make sure that during the punishment phase, J is actually indifferent over the actions in the support, and J will actually randomize over those pure actions. So imagine J has two actions, left and right, and left is always better for J. Then J, if J plays more left, then you need to give J a slightly lower continuation payoff. How much lower? You have to calibrate it exactly such that it cancels out the left-right gap, right? It has to be exact, and that calculation has to be done using the discount factor. Okay, so this immediately makes us suspect maybe there's a problem. Maybe this is not going to be an equilibrium at nearby discount factors. Okay, now this is our question. So knowing discount factors is a tall epistemic order. Okay, so for applications particularly, game theorists might want to, so we think of ourselves as being outside the model and we are asked to provide strategies. And we might want to provide strategies that do not use precise knowledge of the discount factor.
Excuse me?
Yeah.
Sorry, do I understand correctly that the problem is that you don't know how long the punishment phase should last if you don't know the delta exactly?
No, So if you don't know the delta, so imagine, so just suppose that even the punishment phase just takes 1 period.
Okay.
That's fine, okay? But in order to punish you, I need to mix over 2 actions, left and right.
I see.
And
you cannot get indifference when you don't know the delta. Okay.
Exactly.
Yeah.
So
okay.
I will always play left if left gives me 2 and right gives me 1. So then what you have to do is I got 1 extra by playing left. So then the game theorist has to subtract 2 times, 1 minus delta, right? He's going to figure out, oh, this is the bonus you got because you got lucky. And maybe you got lucky, but we're going to remove all that luck because otherwise I'll keep on pretending I got lucky.
Okay. Thanks. Yeah.
So that's the problem. That's the problem. So knowing discount factors is a tall epistemic order. So in many applications, the game theorists might want to provide strategies that don't rely on the exact discount factor. So imagine you're doing a regulation problem. So the regulator doesn't know which exact firms the regulator is going to face, but knows that, okay, the firms are patient enough that given the market interest rate, we can say the firms are, 1 divided by 1 plus R is, at least 0.9 or 0.87. So we know this is a minimum discount factor, but we don't know if it's 0.87 or 0.91 or 0.95. So we want to get, okay, something that is robust in this sense. So international agreements is another one. Heads of state might be changing. You do an agreement today, but you want to make sure that even if the next person wins, right? You guys just had a change of head of state. So this should resonate with you. All international agreements require that this should be robust to such changes. Legislation, for example, legislation, there are parties legislating things. There are many targets of legislation. We don't know their individual discount factors. So that's the kind of, and in some of these examples, a player, for example, in a bargaining situation, a player might represent aggregate agent preferences. So there are a bunch of agents that you're bargaining for. Many, many workers or many, many firms, they have slightly different preferences. Can we get this sort of one-size-fits-all thing to work? Now, we don't want to go down the Bayesian route because somebody might ask, fine, why don't you have, if you don't want to have common knowledge of discount factors, why don't you have, beliefs over discounts and beliefs over beliefs, beliefs over beliefs over beliefs? That kind of thing is very unwieldy. And, I think Shmuel Zamir was, or at least was, and maybe is in the audience, and he's done a lot of work on this topic. And it's extremely complicated. Plus, that also, how do those beliefs come about? And there are many questions that might be asked. We want to kind of step back from those and say, okay, what can we do when we know that players are patient, but not precisely how patient they are? So that's our setting. So we introduced this notion of Blackwell equilibrium. So Blackwell equilibrium is basically something that works for high enough discount factors. That, of course, I'm going to give you precise definitions here, right on the slide, but that's what it basically is. Now, the first version of our paper was called Blackwell equilibrium. We were very excited to get a 2-word title because I've never managed to get a 1-word title, but a 2-word title seemed very good. But unfortunately, somebody has introduced Blackwell-Nash equilibrium for stochastic games, so we can't do it. However, their work is quite different from ours because they are concerned more with existence, right? So in their setting with stochastic games, it's a very non-trivial problem. In our setting, it's not a non-trivial problem because, we have a repeated game. So as long as we have a stage game Nash equilibrium, we can just repeat that. And that's an equilibrium of the repeated game, okay? So we are looking at very different things. But the thing that we are interested in is sequential rationality. They're just looking at Blackwell-Nash. So they're not concerned about sequential rationality, which is something that both the notions Blackwell equilibrium and Blackwell PPE will respect. So let's go over the definitions. A strategy profile sigma is a Blackwell equilibrium above delta, lower bar, which belongs to 0, 1, okay? If sigma is an SPNE of G infinity delta for any delta, right? that is exceeding this delta lower bar component by component. And now this is for perfect monitoring games. And for imperfect monitoring games, we haven't introduced a model of imperfect monitoring yet, but we're just telling you, we're going to talk about a Blackwell PPE, perfect public equilibrium above delta lower bar again, if it's a PPE for any delta with delta I greater than or equal to delta lower bar. So it's the same thing. In one case, it's SPNE, one case, it's PPE, but the same sigma works above delta lower bar, pair by pair, of course. Right? So essentially, you can just stick Blackwell to any solution concept for discounted repeated games. Any questions? Okay, so now that we've introduced the main concept of a Blackwell equilibrium, we're going to continue looking at just a little bit of the motivation behind this. So this is historical reference. We are honoring Blackwell, of course, by extending his Blackwell optimality to, actually, I think the slide should have been called Blackwell optimality rather than Blackwell equilibrium. So this honors Blackwell by extending it to discounted games from single agent dynamic decisions. So that's Blackwell's famous theorem, 1962. Any finite MDP Markov decision process has a stationary strategy that is optimal above a cutoff discount factor. Again, the strategy is optimal above a same strategy above a cutoff discount factor. And this sort of strategy is said to be Blackwell optimal. Now, this doesn't help this doesn't give our result because this is for finite MDPs. Our set of histories is not finite, right? It's an infinitely repeated game. Okay. So in a Blackwell equilibrium, sigma, each sigma I is Blackwell optimal strategy in the MDP that is introduced by, in the non-finite MDP introduced by the game G and the strategies of the other players, so sigma minus I, right? So we have to find simultaneous, so it's not finite, and we have to find simultaneous Blackwell optimal strategies for one per player. Okay, so this is a quick summary of the results. Some of this stuff might seem mysterious because we haven't spelled things out. It's not that, we will spell things out later on. This is kind of a very bird's eye view slide, just to give you an overall picture. So the bite of Blackwell restriction depends on monitoring. Okay. Roughly speaking, as the monitoring becomes worse, when monitoring becomes worse, Blackwell equilibrium has more bite. So the more you can monitor, the more constraints you can impose from outside. So then monitoring the Blackwell constraint is less important. Another way of thinking about this is intuitively, you see, we talked about this earlier, and Bernard asked this question, and I mentioned that the problem is that there is mixing going on, right? So mixing is the major issue. So when you have mixing, suppose you can monitor certain things. Suppose you have perfect monitoring, then you can't see how I'm mixing, but you can at least check if I'm mixing over the right things. As soon as I play something off the support, you say, aha, you deviated, so you can catch me. So then you have ways of detecting some deviations. So then Blackwell monitoring has less bite. As you mixing, as you have worse monitoring, it becomes harder and harder to monitor mixing. So it becomes harder and harder to give incentives for the right kind of mixing. So then fewer and fewer things satisfy the Blackwell criteria. So under perfect monitoring, you will see that pure actions are of course fine. Nash is fine. And some other types of mixing is also fine, but many types of mixing cannot be done, right? Because in the standard perfect monitoring world, all kinds of mixing can be done. There's no problem. You just have to adjust the future incentives. But here, not knowing delta means you cannot adjust future incentives exactly. So then you have a difficulty. Okay. Yeah.
Sorry
yes,
to interrupt.
No, go on.
If you, so you have no statistical test to even check whether mixing is compatible. You might use very bad probabilities with the right support. And you say you cannot detect that. Is that correct?
Right. Even that will not be enough. And the reason is we need exactness. So we want to emphasize the standard folk theorem has a very knife-edge construction there.
Okay.
Right. It's not many of these, statistical tests. If you think of Radner, for example, Yari, Menahem, Yari, Radner, they have lots of work on using statistical tests. Statistical tests typically, tests within a band. You're within this range, but it's going to turn out here. Exactness is very important. Okay, so these things will not work. Okay, now when we go from perfect monitoring to imperfect public monitoring with the PRD, okay, we will get similar action, the same action profiles as under perfect monitoring, and the public randomization device will be useful. And then we will go to generic imperfect public monitoring without PRDs. And then we will see that we can only get pure meaning pure action profiles or stage game Nash actions. So basically, as we go from perfect monitoring to generic PRD-free imperfect public monitoring, we will not be able to support anything more than pure actions and Nash equilibrium. Pure actions you can see are easy because you can make some incentives strict, right? But it's any kind of mixing, any non-trivial mixing is going to be a problem. And finally, in the extreme case, and this is a result that we are still working out some details, but with generic conditionally independent private monitoring and gains with unique pure Nash equilibrium, in fact, we cannot even support pure actions. We can support Nash only, and it's impossible to support less than Nash. So because it's just, that's always there. That was our original motivation for saying there always exists an equilibrium. So we can't get rid of that. Okay. So again, this is yeah. So this is perfect monitoring. So perfect monitoring, we have Grimm trigger strategies, and we've shown this to you before. It's an SPNE for delta greater than equal to 1/3. And in our language, what we want to say, these strategies are a not Bayesian equilibrium. These strategies are a Blackwell equilibrium above delta equal to 1/3, right? Because above this, the same Grimm trigger that I've given you works, okay? So this is just semantics, okay? So now the trick is, let's do Fudenberg. So here I want to emphasize that Friedman already had Blackwell optimal strategies. Friedman already was a Blackwell equilibrium. He just didn't state it in those terms because he wasn't thinking along these lines, okay? So now the question that we have to answer as well, because that's too weak a result. What about Fudenberg-Maskin, okay? How do we incentivize pairs to randomize, okay? So Fudenberg-Maskin strategies require randomization during punishment because it's min-max. So anybody mix min-max and then we need to randomize. So suppose pair I needs to randomize between AI and A prime I, then she must be indifferent between them. So that's the indifference condition. Given AI, so we look at sigma. What is the distribution of actions? What is the distribution of paths that sigma induces, okay? Given that pair I plays AI at time 0, okay? And we can take it at any time, but in particular, let's start with time 0, okay? So then she must be indifferent over these. So this is our equality, right? On the left and right, the only difference is AI on the left, A prime I on the left, and these are the two pure actions that I is randomizing over. They must be equal. So our question is at the bottom of the slide, can we construct continuation strategy profiles such that the difference in continuation payoffs cancels out a difference in stage game payoffs for any large delta? So this is important. We cannot do it for one specific delta like Fudenberg-Maskin. We have to do it for any delta, okay? But that delta we can say needs to be above 0.8, above 0.9, whatever. So let's look at something called myopic indifference. So first, let's take randomization between AI and A prime I, same condition as last page, but now we are going to rewrite it as a polynomial, or actually a power series, right? Because it's an infinite degree polynomial. So it's a power series. It's a convergent power series. Delta is between 0 and 1. Okay, so actually delta is between some delta lower bar and 1, right? So this has to hold for all high enough discount factors, and that's the condition. Now, this is the left-hand side is a convergent power series in delta. Okay, it holds identically for all delta in this range. Then there's the identity theorem from complex analysis, Alforce or wherever you want to look it up. This says that this must be the zero function. In other words, all the coefficients for every t has to be equal. So in particular, for t equal to 0, you get that result. That gi, the payoff of I when I place ai and a prime I, given what the others are doing, must be the same. Right? So myopic indifference, this is what we are calling myopic indifference. Given what players other than I is doing, I must be indifferent at that point of time over all possible pure actions in the support of a mixed strategy. Okay, so this is myopic indifference, and it's a necessary condition. So now let's define script AMI. So script AMI is a set of all these mixed strategy profiles that satisfies myopic indifference for every player. So for every I, for every AI and A prime I, okay, in the support of alpha I, you will get the same payoff from playing AI will get the same payoff from playing AI and A prime I, given what the others are doing. Now, what about pure action profiles? Of course, this holds for pure action profiles because there's nothing to check. It trivially holds. If it's a Nash profile, then for Nash profile by construction, it holds because everything is a best response. All the things that you're mixing over in Nash, they're all best responses, okay? But there are more things in it, not just Nash and pure, okay? Now, why are there more things in it? Well, you can think about AMI, script AMI, as Nash equilibria in smaller stage games. So Nash equilibrium says, whatever you're mixing over, you must be indifferent over. So suppose this is your support, you must be indifferent over things in your support. And these have to be better responses than things outside the support. But now we want to remove the condition that things outside the support have to be worse responses. We say, okay, you might have, this is perfect monitoring. We can observe if you're going outside the support. So we can deter that through the usual punishments. So we don't care about that. Okay. So we are going to give you, so then we will look at a smaller game. So even if those things are better responses, eliminate those. Look at a smaller game in which you have only the rows that we want you to mix over. And then in that reduced game, your myopically indifferent action is indeed a Nash equilibrium of the reduced stage game, right? And this means that we can think of this as Nashes of smaller stage games, right? That's why it contains more things. And our first theorems that we've already proved, which is the necessity of myopic indifference. If sigma is a Blackwell equilibrium, SPNE or PPE, then the strategy that you play at every public history is going to be in script AMI. So it must satisfy myopic indifference. Now, let's define the, so now we still haven't given you a folk theorem. So we have this necessary condition. So we have to give you a new min-max. Accordingly, we will give you the myopic min-max. Okay, so suppose players are restricted to play from script AMI in equilibrium, then player I can guarantee herself at least her MI min-max value. Okay, where MI min-max is exactly like the standard min-max, but you just take min over script AMI. Okay, now notice that script AMI is a subset of all possible mixed strategies. And the bigger the set you minimize over, the lower the minimum is. So the standard min-max W is lower than WMI. Now I should have put, I throughout because we are looking player by player, but that's fine. Then look at N, Nash equilibria. All Nash equilibria are, and all pure action profiles are in AMI. So the pure one and the worst Nash are weakly bigger than mixed, than the myopic indifference one. So the myopic indifference one lies between, pure and Nash. Okay, it's lower than that, and it's higher than the standard min-max. So it's in between. And actually, we can show, I will show you through an example that it's actually, you can make these strict. And let me state the Folk theorem for you. The perfect monitoring Blackwell Folk theorem states every Blackwell equilibrium payoff vector V satisfies that for all I, Vi is greater than or equal to Wi myopic indifference. So every player must be getting more than her myopic indifference min-max value. The proof is very similar, exactly similar to the standard result. You can just deviate at every period, then you cannot get worse than this in the repeated game. Conversely, as F is full dimensional, V is in F, so F is a set of feasible payoffs of the stage game, V is in F, and every I gets more than the myopic indifference, so the only change is we've added the Mi on top. Then V is a Blackwell equilibrium payoff above some delta, or delta bar if you prefer. So this is exactly the same as the standard Folk theorem, except that the standard min-max has been replaced by the myopically indifferent min-max. Okay, and I want to say two things. We are using full dimensional F, and full dimensional F simply means you have enough players, you have enough dimensions in the payoff set as you have players. So it's possible for me to reward one person and punish the other people. So increase one payoff and decrease the other payoffs, or increase two people's payoff and decrease the third person's payoff. So we can independently reward and punish the players. They are not tied together. Okay. And is there a question?
I actually have a question about, so what do you mean exactly by a Blackwell equilibrium payoff factor? Because the payoff factor may very well depend on a discount factor delta for fixed strategy profile.
Right, very good question, very good question. So I should have clarified this. So by Blackwell equilibrium payoff vector, I just mean that so one notion that we use, it's just the payoff, okay, of the Blackwell equilibrium that we've picked at a discount factor above that.
Oh, at one particular, okay. Mm-hmm.
But we can also do limits. So we can also do limits. So not every so if you fix an equilibrium and you let delta go to 1, it's not clear, even if it remains a Blackwell equilibrium, the payoff could change. Yeah. And it's not even clear that the payoff has a limit, right? Mm-hmm. So that we might think is a problem. So we can also deal with that case, okay, by coming up with a different construction. We can construct equilibria in such a way that they actually have limits as delta goes to 1, and that limit will converge to the V that we want as delta goes to 1. So that would be the more satisfactory notion, perhaps. But yeah, we can do that. We have an extension that does it.
Mm-hmm.
Okay.
Okay, thank you.
Thanks. Conversely, now, so full dimensionality we talked about. Okay, so one thing I want to emphasize here is that we don't have a PRD, so we are not using a public randomization device, because this is relying on another paper of mine joined with Oni Dasgupta. So what we do in this paper, we show how to construct action paths such that with a target payoff, so we have a target payoff V, we show how to construct an action path that stays arbitrarily close to the target payoff. So not only do you get V, so suppose F is full dimensional, V belongs to F, and you fix an epsilon greater than 0, such that a small ball of radius epsilon around V is in F. So then we can show that for any high enough delta, we can find a sequence of action profiles, AT, that gives, at that delta, it gives V. And for all continuation payoffs are going to be bounded by epsilon. So it never goes too far away. Okay. So this is we introduce a set theoretic property called self-accessibility that we define, but I don't want to go into it here. It's going to take us too far from it. And finally, we have a corollary of Frobenius's theorem, which I'll just tell you what this says. It says that suppose there is a sequence X of payoffs, right? So these are per period payoffs, such that the discounted payoff for every point tau onwards, it's between A and B, right? Then if you raise the discount factor to delta prime, it's still going to stay between A and B. So now you can think of this previous result as saying we can keep continuation payoffs within a ball. And the next result says, well, whatever the ends of the ball are, you can keep it within that. So you can keep it within a cube. Even if you vary the discount factor, you can keep it within the cube that just encloses that ball, the hypercube with axes parallel, with sides parallel to the axes that just encloses the ball. So basically, and this is also related to the Arrow-Levari stopping theorem. So that's a result on when to discard a security. And it says that, if your patience increases, then you're not going to discard the security earlier. So you have a security that gives you positive, negative payoffs, okay, flow payoffs, you can get rid of it anytime you like. But if the discount factor increases, you're not going to get rid of it sooner. So this is basically a version of that. They both come from some version of Frobenius. So putting these two together, we have the following. For all I, for all delta prime, that's greater than delta. For all tau, we have that the continuation payoff there is between Vi minus epsilon to Vi plus epsilon. So this defines a hypercube. Okay, so just repeating, but DG construction, continuation payoffs stay in the ball, epsilon ball around V. Patience lemma then guarantees that the continuation payoffs at higher deltas, not just that particular delta, so at higher delta primes, will stay in the smallest hypercube containing BV epsilon. Okay, now why is this important? This is useful because we want to keep continuation payoffs close by. You see, the whole thing is we want the payoffs to be ranked. We want to have a construction. Think of the Fudenberg-Maskin construction. The construction has a feature that if you punish, it's better to punish a deviator than to be punished yourself. Because if you punish a deviator, you're going to get a reward epsilon at the end of the punishment. Okay, so that's better. And we want to now keep the ranking intact. We want to make sure that the continuation payoff does not go away too far from the original target points so that we can repeat a construction similar to Fudenberg-Maskin. So again, on path, we will play a sequence of pure actions that we get from Dasgupta-Ghosh. This will give us the value V at that discount factor. If I deviates, then we will myopically indifferently min-max I for a certain number of periods. Then we will reward the punishers, but without regard for how they punished. What does this mean? This means that we will not take into consideration how they mixed during the mixing phase. Okay? Because we've already made them myopically indifferent, so we don't need to take into account how they mixed. We don't need to adjust the future values in the continuation payoffs. So we can regard them without thinking about this. Of course, if there are observable deviations, then we punish, right? If you go off support, then we punish. But if you're on support, we don't worry about, how you're about your mixing. Okay. Now, in order to do this, in order to make sure that it's still better to punish than to be punished, we have to make sure that continuation payoffs don't go too far away. And this slide just told you the continuation payoff will not go too far away. So then the relative ranking of all the points is going to be preserved, and every player will say, I'd rather punish the other person than be punished myself. Okay, and so everything is myopically indifferent, so we have the Blackwell property. Okay, so now I have a slight problem. I want to draw this for you. So I think I'm for a second going to go off video, and excuse me for a second. Okay, so this is a figure I want to show you. Okay, so this is a stage game. Okay, so we have 0, 0, we have 1, 0, we have 1, 1. We have.
I don't see anything you're drawing. I mean, maybe others do, but I don't.
Okay, this is completely my fault.
Maybe the screen should be shared from the other device.
Right, so that's what I'm doing. I'm sorry, I'm just, yes. So these are the points. Thank you. 3, 0 and 0, 3. Okay. So this is of course Nash equilibrium. Okay. Now, 2's min-max, the way we have done it in everything is equal to 1. Okay. 1's min-max, so this is the Nash payoff, NE. Okay. The feasible set is, of course, you join all this, you join all the points. That's your feasible set. That's F. Okay. And this is the worst Nash point. And now if you look at, okay, so 1's min-max. So for this, 2 is going to play half L plus half R. Okay. And this will give 1 a payoff of 1/2. Okay. So this is 1/2. So then the min-max is able to support this whole set. Okay, that's min-max. Right, so this is min-max. This is the standard folk theorem. Okay, now Friedman is here. This is Friedman. And in our case, but notice this R is always a dominant strategy, okay, for player 2, and mixing half-half by player 2 is actually not myopically indifferent. There's no way you can support this, and we can show, and you just take my word for it, but we can show that when 2 mixes 3/4 L plus 1/4 of M, this gives a payoff of 3/4 to 1. Okay, so we get this point 3/4. Okay, and this is our set. So this is our set. Our set is everything above this. So in particular, this region from the Pareto frontier is out. These payoffs are also out. They cannot be supported. So this gives you an actual example where our strategies and our construction have bite. Okay, so that's the one I just did. I hope you can see my slides. Okay, so let me spend the last few minutes talking a little bit about imperfect monitoring. So the basic notation, so there's a finite set of signals Y, and pi is the monitoring function. It's a mapping from actions to mixed distributions over public signals. The primitive utility is a function of your own action AI and Y, and it maps from there to R. GI is the expected utility, because that depends on everybody's action, but you cannot learn anything more because you ultimately get UI of your own action and Y. So by seeing your utility, you learn nothing more. And we're not going to deal with private strategies which can depend on your own AI, but we are going to deal with, we are not going to deal with private strategies that where you can where your strategy depends on your AI. We will deal with public strategies only. So it depends on the sequence of public signals. Okay. Now, let's look at a folk theorem with public randomization. Okay, much is possible with public randomization. We have a clean characterization only when monitoring has a product structure. So product structure means a public signal actually has n components, and each component, the ith component, is generated by the action of player I, and these are all independent. Okay, so that's the equation out there. We are going to assume that pi I has individual full rank. Okay, so this set of vectors is linearly independent. Okay, and then we are going to define a folk theorem with public randomization. And again, for this, we have to define a myopic min-max. Okay, so, well, a new myopic min-max. And this is defined using a standard kind of, Fudenberg-Maskin or Matsushima algorithm. So a scoring algorithm. So look at the expression that is being minimized. It's today's payoff gi alpha plus some normalized continuation payoff xi of yi. Okay, that's the total. That's being minimized, subject to the actions being in AMI. Okay, and the subject to the inequality. What is the first inequality? The first inequality says I is playing a best response. So when I plays according to alpha, I is playing a best response. And the next condition says xi yi is non-negative. Well, if this is negative, then it means you can drive the payoff still lower. So then you're not at the minimum. At the minimum, this should be non-negative. So if you minimize I's payoff today plus continuation in this way, subject to everybody using actions from AMI, then we get our min-max value. And we get a folk theorem that says if this public randomization product structure and individual full rank, then every Blackwell perfect public equilibrium payoff vector V satisfies that Vi is greater than or equal to this value. And if you give me any vector V that is in the interior of the set F, subject to Vi being greater than or equal to this value, then we can support that value as a Blackwell perfect public equilibrium payoff vector. Now, why do we have interior? Well, because we're going to use self-generation style arguments, and that works for the interior. We will approximate it from inside. And greater than equal doesn't matter because we are taking interior, so we might as well have taken greater. Okay, so again, we have a fairly permissive result. Now, how many? I think I'm over time. Is that?
Yes, Sambuddha, I fear that our time is up. Okay, so do you want to wrap up things?
So maybe you can give me a couple of minutes.
Yeah, sure.
Okay. So basically, I just want to tell you very quickly about the proof strategy. The proof strategy has two things in it. One is that we create a robust equilibrium. So we create an equilibrium that is robust. So look at the construction point 1. Point 1 says that is a perfect equilibrium for all delta belonging to some small interval delta 0, delta 1. And then what we do is reboot. Now, what is reboot? Reboot means we have a public randomization device. We can toss the public randomization coin. And if the coin comes up with a probability number less than P, then we just forget the whole past history. So this changes the effective discount factor. So then we can shift the range of rebooting from delta 0, delta 1. We can basically divide by delta 1 and reboot it up to this value. So then we can take a locally robust equilibrium and reboot it up to a Blackwell equilibrium. Okay, and then I'll just go to the last slide and just tell you this one. So if we have no public randomization device, then if sigma is a Blackwell PPE, then it involves no non-trivial randomization. That is, for every public history, sigma H is either a pure action or a stage game Nash equilibrium. So you cannot even do the myopic indifferent ones once you have no public randomization and generic public monitoring. So the combination of imperfect monitoring and the lack of a public randomization kills all non-trivial mixing. You can only get pure actions or stage game Nash. And I think we can conclude with that.
Thank you very much, Sambuddha. Are there any questions?
I have a question.
Hi, Gary.
Hey. I can see why the need to balance out the outcomes of randomizations is very tricky and actually impossible in case when you're aiming for a specific payoff. But when you go for the min-max, actually you just need to be close enough to the min-max. And at least there is at least one paper that considers such a strategy without all the fine-tuning of balancing. This is one by Olivier Gosner about finitely repeated games. I'm not so sure. There he uses statistical tests. I'm not so sure how easy it is to rule out this kind of structure here. Maybe you know of it.
So,
already thought of it.
Yeah. So actually, I should take a closer look at the paper. But my impression is that so what happens there is he has incomplete codes. I think this is related to his incomplete codes. So he basically has, indeed, he's approximately min-maxing, but then after, there are some stages that he's not specifying fully. And those stages he can later specify using precise knowledge of the discount factor, but keeping the overall structure the same. So we actually have no freedom to do that. We completely deny ourselves any freedom to have any part that is fine-tuned. I think he allows himself some freedom to fine-tune certain things.
I think what he doesn't do is to give complete instructions for the equilibrium.
Right.
It's something
right.
like you can achieve at least this and that if you use this and that strategy. And if everybody achieves this and that, then we're very close to where we want it to be. So
that's right.
Yeah, with this you're right. Yes.
More questions?
Yeah, I have a question on the terminology of this you use the name Blackwell to refer to Blackwell optimality in Markov decision processes, right?
Right.
That's your that is a pure strategy. Are you also using a pure strategy here? I mean, I wonder whether the name is so informative. That's what I'm aiming at, because
I
maybe
see.
you could either call it Blackwell optimal equilibrium, or just maybe say something uniform or discount independent or optimality. I think that would be more informative than Blackwell, because there's more than one theorem by Blackwell that people could associate.
Right. So actually, if it's uniform, so there's some work that's been done, and I think Elon should be the one to talk about about uniform, because he's the expert. He has work on that. But yeah, I understand your concern, because we don't have pure actions necessarily. So but we didn't want to. I mean, on path we play pure actions, but off path we could have mixing. And of course, in the other phases, in the public monitoring phase, that the public monitoring scenario, we could have mixed actions being played. So it's I mean, but we thought that this is sufficiently close to Blackwell in certain senses that we are capturing the sort of essence of the Blackwell-ness.
Yeah, and do you use the proof at all, or do you just use the name? I mean, that's another question. I mean, do you?
We just use the name. We don't use this proof in any way.
I would rather go for a more informative name than a name.
I see. Yeah, I think we were also led a little bit by the fact that the name is catchy.
Yeah, I know. But I mean, then even Blackwell optimal equilibrium would be, still catchy, I think.
Okay. Elon, you have something to add?
So indeed, we thought about it, whether to call it Blackwell equilibrium or mention uniform equilibrium. Now, Blackwell equilibrium is an equilibrium that is equilibrium for every discount factor sufficiently close to 1.
Yeah.
It is true that in MDPs there is a pure Blackwell equilibrium, but essentially there could also be non-pure Blackwell equilibria. So whereas uniform equilibria are usually you will refer to uniform epsilon equilibria.
No. And in this
but
here we have uniform zero equilibria. So it is also different than uniform equilibrium.
No, I know. But I mean, but I would maybe call it, discount independent or something. I mean, so if we call that's the key. I mean, that would be my suggestion. But anyhow, I mean, it's just a question and suggestion.
Yeah. Okay. Thank you very much.
So if there are no questions, I'd like to take 30 seconds and say something. So thanks. Any more questions? Okay, so thank you very much for the invitation. Okay, I really enjoyed speaking here. But I also want to take some time to thank my co-authors, actually, because this paper came about through a merger of a project between Costas and me, and one between Johannes, Satoru Takahashi, and Elon. And they were very kind and invited us to join, and then we merged the paper. And I think the outcome is a lot more comprehensive. So very grateful to them as well.
Okay. So thank you very much, Sambuddha, for this interesting talk and very clear talk. I thank you all for joining us in this, this year. And I hope that we meet again in September, and have a great summer.
Thank you. Same to you.
Yep.
Bye, everyone.
Thank you. Bye-bye.
Goodbye.
Bye-bye.